But you don't do that to the you don't have one more the addition. Okay, guys, what of the homework would you like to see work? Yes.
55 on the other night, not last night, but the other night.
Absolutely, 55. Okay. Let's just kind of put the list of what we want up here. We'll try to work it in some kind of order. Anybody have anything besides 55? 73. 73?
And 53C.
Anybody else have anything they want to add to our 77? Okay, so let's look at 53C first. Okay, who wants to eat breakfast, which refers back to exercise 49? Okay, they want you to make a Venn diagram. Oh, okay, so you just need the C part, which has to do with the complement business. I guess your Venn diagram on 53C looked and I call this my eats breakfast regularly. And then on this side, I was talking about males. Of course, that's the intersection of the two. And then 165 are those that don't fall into either one of those categories. So, obviously, we're looking at females who don't eat breakfast regularly. So 53C, it would look like this. The complement of regular breakfast eaters is not regular breakfast eaters. And the complement of male, which that's what that little C means. It's just the complement. It's the what's not. So the complement of males is females. So we're looking for the intersection of those who don't eat breakfast regularly and are female. And obviously that's that 165 in the bottom right of your Venn diagram. And that was a good one to work. I appreciate you asking about that because of the complement notation. And that's all that little C means is what's not. So the complement of eating breakfast regularly is not eating breakfast regularly. The complement of male is female. That 53C okay? 55. Who asked about? Was that you too? Okay, what part did you need to see the table or what part of that?
I couldn't get a table at the end because I couldn't get the table. I couldn't do the either.
Gotcha. So how about I set the table up for you and then kind of let you try to work through the problem? Would that work? Okay. So here's what my table looks like. Maybe two many lines, maybe not. So we had a MySpace and a not MySpace. And we had a Facebook and a not Facebook. And then I had totals. Ended up being 20 million. If you want to come out, if you don't want to write all those millions, you could come out to the side and say this table's in millions, and you could just write 20 and 8.4 and 2.4. It's up to you. table, and that should, help you set up the Venn diagram and the, probability statement. If you need me to work B and C, I will, but you think from here you can do.
Yes.
Does anybody need me to stay on this for a little bit longer while you're putting the tables together? Let's look at 73, which I think is going to be in a different section entirely. If it is. Oh, I was so glad. I was hoping. Who asked for 73? Awesome. This is a really good thinking question, and it also helps you with the conditional piece. So let's look at 73. And we've got 4 things going on 73. We've got the probability of being taught. We've got the probability of being a professional basketball player. We've got the probability of being tall. Given that, we know the person's a professional basketball player. And we've got the probability of being a professional basketball player given that we're tall. Okay, so let's just start talking about these. Probability of being tall. There's no conditions on that. We're looking at everybody in the world. What's the probability of being tall? I mean, let's just look around our room. You know, what's the probability of being tall? I don't know. 20, 30%, I'm guessing. Doesn't really matter. I'm just thinking right now. But that's what that probability is asking. What's the probability of being tall while you're a human? No conditions on that. Okay, so we're thinking, you know, there's something, it's not that unusual for somebody to be tall. What about the probability of being a professional basketball player? I don't personally know any professional basketball players. Even if there's 10,000 or 20 or 30,000 professional basketball players, that's a very small percentage of people in the world. So can we agree that this is very small? Okay, so, and again, there's no condition, so the sample space is a human around the world, right? There's some conditions on this one. This is a probability of being tall, given that the condition of being a professional basketball player has already occurred. Your denominator down here, your sample space, is the fact that you're a professional basketball player. So our sample space is not that big. And among those, so in your mind, that you're professional basketball players, what's the probability that you reach in and grab one that's tall? Yes. As a matter of fact, it will be unusual if you reach in and pull somebody out that's not tall, because a lot of times they'll make the highlight reel. They'll go, look at this professional basketball player. He's only 6'2", or whatever, you know, he's not that tall. So this one is pretty high. Okay? Now, different sample space. What's the probability of being a professional basketball player, given that the fact that you're tall has already occurred? So now our sample space has changed to tall people. So think of all the tall people you know. How many of them are professional basketball players? I don't know any. I mean, I'm sure if I got on, maybe I can find one. But our sample space has changed to tall people, and of those, so now we just got to figure out, put the very smallest probability first. So we kind of got an idea of where we're going with this. Of these 4, which one do you think is the least likely? Okay. Probability of being a basketball player is probably the very smallest. And I'm going to say that this one's probably the next smallest just because there's not a lot of professional basketball players. We've limited the sample space to tall people, but among tall people, there's not that many that are professional basketball players. So I'm going to say this is probably the next smallest. We've already said that this one we thought was really high, so we can put that there. And we've used everything but probability of being tall. So this is the order that I put mine in. Does this kind of make sense to you since we talked it through? Thank you for whoever asked for that. That was a good example of how to deal with those possibilities. Okay, 77. This is another good one. So 77 is asking you to make a tree diagram. It says you have a box with 20 chocolate candies. Okay, so I'm starting out with candy. And what can happen when you reach into the box of candy? You can either get a soft center or a hard center. So the probability of getting a soft center, they said, is 14 over 20. 14 over 20, that means we're looking at 6 over 20 here. Okay, so I'm kind of just getting the idea of how to do a tree diagram. But it says, what's the probability of choosing 2 candies? I'm just showing the probability that would happen if you chose once. Right? I reached in one time. Okay. Now I've got to do another branch and show what happens the second time. So let's say I reached in that first time and got a soft center. What can happen the next time? Well, let's go work off this branch. Here's me reaching in one time and pulling out a soft center. Okay, well, I could get a soft center again, but there's not 20 candies in the box, there's only 19 now, and if I had gotten a soft center the first time, there's not 14 soft centers anymore, there's only 13. Okay, I could reach in, get soft center one time, hard center the next, there's still not 20, there's 19, but all 14 of the hard centers are there. I mean, all, that needs to be a 5. Sorry. I mean, a 6. Because whatever's here and here needs to add up to your denominator. That's one possibility. I could have reached in and got a hard center the first time. That means there's only 19 candies left, but this one's going to be. So that's the tree diagram describing reaching in twice. Is that okay? The only thing is you got to remember to subtract out correctly and make sure your numerator is added to your denominator. That's not even a question though. The question is, find the probability that one of the chocolates has a soft center and the other doesn't. So we want the probability that one has a soft center and one has a hard center. So we look at our tree diagram and we try to figure out ways that can happen. Okay, so soft center, not interested in that. Soft center and hard center. Okay, this is one way that it can happen. Hard center, soft center, here's another way it can happen. We're not really interested in this one because the problem didn't ask for that. Okay, y'all remember how to get that number right there? Multiply. You multiply along the branches, you add down the branches. Because you're wanting, see what word that is? And. So to get this number, you add, you multiply. Okay, and that, I'm going to kind of crunch the number for you. If you put that in your calculator, you're going to get 0.2211. It can happen this way. Notice the word I use here. Or another way I can get a soft center and a hard center is if I got a hard center first, soft center second. So multiply. Okay, so the probability is 0.2211 plus 0.2211 equal to, you want to go 3 plus. Just remember, you're multiplying this way and you're adding this way when you're working with it.
So you have to add all your probabilities?
that give you the option that you're looking for. If there had been another way to get soft center and hard center, I would have had to do that, but there was only two ways to get it. So the reason I chose to multiply where I did, I looked, okay, soft center, hard center, this way will give me what I want. So that way. Anything else on the homework?
91.
91? Let's do our notes today. Actually, 89 and 91 should have been with tonight's homework. We kept pushing about 89 and 91. What about, when I was looking over them this morning, I wondered about a few of these. How about, 63, 65, and 67? Did y'all have any questions with those? The conditional? Awesome. Okay, wonderful. Thank you.
Okay, 83 now.
Could have just shown y'all 83. There's 83. No, I'll put that back up for you. Maybe we'll have time for it. Okay, politics and ice cream. Suppose 500 college students are asked to identify their preferences and political affiliation. I'm on page 6 of our notes, last page. They're going to identify themselves as Democrat, Republican, or Independent. And what flavor ice cream do they like? Chocolate, vanilla, or strawberry? Fill in the table in such a way that the variables political affiliation and ice cream preference turn out to be completely independent. In other words, the conditional distribution of the ice cream preference should be the same for each political affiliation. And the conditional distribution of political affiliation should be the same for each ice cream flavor. Okay, I tell you what I'm going to do for this one. I think we're just going to fill it in, and then we'll show that it's independent. I think that's how I'm going to do this one. So we're going to put 81 here, 36. If you were doing it and you didn't know, you probably would have started here because since you know it totals to 500, it's going to give you 180 there. And then kind of work backwards. Let me give you a minute to fill that in. It's really neat if you do it with knowing that it's independent, but it takes a little bit longer than I want.
So we don't want the ice cream numbers to like affiliate with your type of political.
Correct. We want them to be independent of each other. So it doesn't matter if you like vanilla. That you liking vanilla will not influence whether you're a Democrat, Republican, or Independent. And that's ridiculous. I know when you think about it with your head, but in statistics, you can't tell if something's independent or not until you kind of crunch the numbers. So you can't look at it and say, that's ridiculous. I know that's independent. Although we made it to be independent when we set the table up. Let's just kind of crunch the numbers. The way you prove that something's independent, do y'all remember how to do that? Right. So you can just simply start out and look at the probability of being Republican. What's the probability of being a Republican?
180.
Okay. If we're looking at independence, then the probability of being a Republican, given that you like vanilla, would be equal to this 180 over 500. Well, is it? Well, in this one, we've limited our sample space to people liking vanilla. This given that means this is something that's already occurred. We're only looking at people that like vanilla. So, how many people like vanilla? 200. And out of those 200, how many identify themselves as Republicans? Okay, now you got a kind of a calculator exercise. How close is it? Oh, just by looking at it? It should be the same, yeah. So that's how you prove independence. Because the vanilla thing has no factor on the Republican. It's exactly the same. Whether you look at just Republican or Republicans, given that they like vanilla. And you could go through the chart and do the same thing with Democrats and chocolates and so forth with all the categories. I think you got. Do we have the idea on this?
So if they're not equal, they're not independent?
Correct.
So if it was .37 and .36,
We would have to, at this point, say they are not independent. But how close is close enough to call them independent? We will learn in a couple of months. At this point, if you don't get the exact same number, you're going to say they're not independent. The fact that they give you the same number either way lets you know that this vanilla has no impact on party affiliation.
So if you get the same number, it doesn't matter.
Do what?
So the same number means no impact.
Correct. Locking the vanilla, that's the thing that's already occurred, and it had no impact on the Republican things. And the way we filled out the table, you'll be able to do the same thing with, say you wanted to check about being a Democrat. You just find the probability of being a Democrat, and maybe we want to, and that's how you were supposed to fill the table out. You were supposed to find the probability of being a Democrat and then create a ratio that was equal. But I just did it this way this time. Probability of being a Democrat, given that you like strawberry, you're going to get the same ratio in both places. You look, Landon, is there something I can...
I mean, yeah, I get it.
You have to kind of think about it a little bit. You have to realize that this happening has no effect on this, and that demonstrates that I give you the same number, the same percentage. Because think about it. What if you had looked at people that like vanilla, and given that they like vanilla, they're Republican, what if instead of 36%, that was 76%? Would that help you see that liking vanilla and being Republican are not independent of each other? If this number was like a lot bigger, like twice as big as this number? Okay, I'll let you. We're going to shift gears just a little bit from independence to a little bit different topic, not much, but in baseball, this is where I'm at, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning about 40% of the time. So to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. What is the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance in other innings? So we want the probability of a perfect 9 innings. And we're making a big assumption here. We're assuming they're independent. And we'll talk about why that's probably inaccurate. But we're going to say that because we can say it if we want to. If they're independent, how would we get that probability? I counted correctly, wrote that 9 times. If they're independent, it's that easier thing that we first started learning how to do. And when we think, and we multiply, 1 perfect inning, and the next perfect inning, and the next perfect inning. So we're multiplying. Now you would probably, I just did that to kind of demonstrate, most of the time you're just going to want to use to the 9th power instead of writing that 4 times. But assuming independence, the probability of pitching a perfect game is that not very high. You know, fatigue and nerves and conditions and, you know, a host of other things lets you know that one any is not independent of the other. So I would assume that, how often do pitchers throw perfect games? In a career, a pitcher might throw, do they?
Not every pitcher, definitely not every pitcher.
Okay, so even though this number is low, it's probably too high. Because I know a lot of times when
It wasn't a perfect game last year.
okay, so that helps me. That helps you. Because I know I don't watch that much sports, but you always see those. If anybody ever does, they make a big deal out of it. So I know it happens very much. Okay. The first trimester screen, we're going on to kind of a different example. There's a non-invasive test given during the first trimester of pregnancy to look at abnormalities in the fetus. According to a study, 5% of normal pregnancies will receive a positive result. So let's make sure we understand what happens. You have this test, the baby's normal, but 5% of the time it'll say it's not. So we call that a false positive. Among 100 women with normal pregnancies, what is the probability there'll be at least one false positive? So we want to write our probability statement to get full credit, so we'll say the probability of at least one false positive. And the whole point of adding this example is to let you know in statistics how to translate at least one. I'm going to ask you to kind of flip it on its ear. So the probability of at least one is 1 minus the probability of none, or no positive results. And I'm going to stop once you write that down and make sure that that makes sense to you, that those statements are equivalent. At least one is equal to 1 minus the probability of none. It's called a complement. Does anybody need help interpreting that or making sure? If you had an example of 5 people, and you were looking for at least one to have something happen, that means you're looking for something to happen to at least one. So that would be 1. At least 1 could include 2, right? At least 1 could include 3. At least 1 could include 4. At least 1. And if I'd started with 0, if I'm looking at least 1, the only number I haven't included is 0. So if I do 1 minus 0, it'll get me the same thing as 2, 3, 4, and 5. Well, let's actually crunch the numbers on this. What is the probability that there's 5% of the time you're going to get a false positive? So are you okay with me substituting here with since it happened none of the times, the 100 women went through, none of them got a false positive. So. And I didn't crunch the number on that. And to me that's really interesting because that will pretty effectively affect your life if you get a false positive. And the probability of it getting at least one false positive, well, most of the time when 100 women go in, 5 are going to get a false positive. And then they have to go for a second test. So that's pretty impactful.
What's the probability of them getting a false positive on their second test?
We're going to actually work a problem like that, and unfortunately, it's pretty high. And it's the same, well, I say relatively speaking because we're talking about people's lives. It's the same thing with drug testing. False positives, they make it where false positives are more likely because they want to err on the side of catching people. See what I'm saying? In my opinion, I don't know. Okay, so yeah, that doesn't work for drug testing. 99% of the time, out of 100 women, you'll get at least one false positive. That's pretty. And you think 100 women? No, I do know 100 women. So I think that's pretty impactful. Okay. What is the conditional probability formula? Okay. So we kind of talked around it but here's the actual conditional probability formula, and it is on your formula sheet. So what if they ask it in such a way that we want the probability of B given that A has already happened? We've used it a little bit in the AND formula, but we haven't just found the conditional by itself. It's a probability of A and B divided by the probability of A. We had to have this to write it on our formula sheet, though. How is it related to the general multiplication rule? Well, here's my multiplication piece. All it is just rearranged. If I want this part of it, all I have to do is multiply both sides by this, P of A. You know, obviously one formula came from the other. It just depends on what piece you want to look for. It's just like when you have x's and y's, and sometimes you want the y's and sometimes you want the x. On this one, sometimes you want the probability of A and B, and sometimes you want the conditional probability. It just depends on what piece of the equation you're asking for. What is a very common way to lose credit on probability questions? No work. So what I'm going to ask so that we get the right practice, you always put a probability statement which looks like this. You don't have to get fancy. If you can't remember the symbols, write the word and, write the word or, no problem. Copy it out and stamp. You got to have this. You also need a fraction. You need a number on top and a number on bottom when you're looking at even simple probability. When we graded the free response, last year there was one on there, and people went straight to the decimal. They got a P instead of an E. That's unfortunate because their decimal was correct. But for some reason, that's part of the rubric sometimes, if they want to see where the decimal, you're better off putting the fraction and leaving it unsimplified than you are changing it to a decimal and not showing where the decimal came from. So that's just a tip. Let's do the drug testing one, try to get that done because it's actually really interesting. This is drug testing one. False positives in drug testing. Many employers require prospective employees to take a drug test. A positive result on the test indicates that prospective employees use illegal drugs. However, not all people who test positive actually use drugs. Suppose 4% of prospective employees use drugs. False positive rate is 5%, false negative rate is 10%. Okay, well, that's actually a little bit different than what I was thinking. So, let's start out. Let's do a tree diagram. And what are we talking about? We're talking about prospective employees. And they either use drugs or they don't use drugs. So, use drugs or no drugs. Okay, 4% of prospective, can't say that, employees use drugs. So the complement of that would be the 96% who don't. Now, you sat down to take the drug test. What can happen? The false positive rate is 5%. False positive means you don't use drugs, but you got a positive result. So let's go down to the no drugs section. 5% of the time, you're going to get a positive result. 95% of the time, you're going to get a negative. You're like, oh shoot, you know, 100 people go in, 95 of them get the right result. Well, you may be one of the 5. You're one of the 5. The 5% sounds a little bit bigger. Okay, false negative rate is 10%. That is different than I was thinking because the false negative. That means you use drugs and 10% of the time they don't catch it. So, use drugs. 90% of the time they're going to catch it. 10% of the time you're going to get a negative result anyway. And I don't know how accurate that is. That just could be people outsmarted or whatever. questions so far about how I'm making the tree? I just start out with my sample space, whatever that is, and kind of work through it. What percent of prospective employees will test positive? Okay, so now you got to go back to your tree and you got to find all the pathways that will end up with a positive result. So I'm going to do that in blue. Here's positive. So that and that's a path. Here's positive. So that and that's a path. Do you remember what we do to these two numbers to get our resulting number?
You multiply.
Awesome. So if I multiply, I get 0.036, and here I get, and I can crunch those numbers for you, I'm confident. So the probability that you will test positive, and remember going down, you add, is 0.036, or you could do it this way. The probability that you go in and test positive is about 8.5%, and remember only 4% of us actually use drugs, so twice as many are testing positive than actually use drugs. So, Bonnie, to get your next, what did you say? You get 2 false positives. Okay, so a false positive is no drugs and you got a positive. You would do another branch out here and do positive and negative, and that would give you the probability.
So it would be probably 95 or
Mm-hmm. And that gives you that probability, and it's not as small as you think. And what's interesting, like my husband works at it's at the coal plant too, but at nuclear power plants, if you have an accident, even if it's totally not your fault, maybe somebody messed up and walked in front of you or whatever, and you're a crane operator, you get off your thing, you go take a drug test, and you stay home until the drug test results come back. That would be common practice.
That's how it is at most factories.
And so, say 5% of the time, that person's sitting there, of course, it's only 5% of the times where an accident has occurred, you know. Well, they're going to get a false positive. You don't get to go back. They can request, legally, you can request another drug test, but you're out of work until that next drug test comes back. So to me, that's kind of interesting, and it is impactful because you get back pay if it turns out that you were not using drugs, but, you know, it is, I would imagine, stressful. Okay, the next thing, the B part, what is the probability? And we need to look at the question because you're going to have to write these yourselves, and I want to make sure you can. What percent of prospective employees who test positive actually use illegal drugs? Okay, so you know you need a big P for your probability statement, and this is a conditional probability statement because something has already happened. What is that thing that's already happened that goes after your given statement? Awesome. I was wondering if y'all could catch that because it won't be in a nice, neat place like it always is. Sometimes you have to look for it in the middle of the problem. So testing positive has already occurred. That's all we're looking at. You always look for the action or what's already happened. They've already tested positive. What probability are we looking for? We're looking for them using drugs, given that we already know they test positive. So remember, that's going to be our denominator. Have we already found out the probability of testing positive? Yep. 0.084. And what's the probability that you use drugs, given that you tested positive? 0.036. And so that'll give you, if you crunch that number, 42.9, which is and this came from right here. Because we weren't looking at all the people, that's why we didn't use the 4%. We weren't looking at all the people because they didn't catch all of them. That's interesting. tomorrow. If you, are worried about the quiz, let's find your boost and kind of figure out, we can talk about what's on it, I'll be glad to do that. Do y'all prefer shorter quizzes that count more, or would you rather have a longer one that counts less and gives you more of an idea?
Longer.
Longer?
Like, yeah, like.
More like okay. So I may just do one that has 4 or 5 multiple choice and one for each, kind of model the system. You can do that.
Could you put 83 up, please?
Absolutely.
I get that.